Uh, I'm going to talk a little bit today about how how we see trading systems being implemented, in the next 1, 2, 3, 4, 10 years. Um, we've seen over the last probably 5 years a number of the proprietary trading firms and advanced, people who are using advanced technology to implement proprietary trading. We've seen a real trend towards using FPGAs to do that, and I'm going to give a couple of sort of insights and a couple of little thoughts that I think about how these things are being implemented now, how they're likely to be implemented in the future. It doesn't really just apply to prop trading, though. We're talking about matching engines, pre-trade risk, and various other things. So this really very much falls under the trading technology side of this conference. So I'm going to talk about how to implement trading systems on the Switch and why you would want to do that. So first of all, some basics. I thought about it. Not everybody here who will know who Matamiko is. We're the leading vendor of network switches, effectively, for high-performance trading firms. You go and look in any of the co-located data centers, you'll walk around and you'll see a whole pile of our devices blinking at you from all of the racks there. We're effectively connecting the trading firms with the exchanges. That's our first set of customers, our first use cases were all in ultra-low latency, and we're very successful at selling those sorts of solutions. Since then, we've built out our portfolio of products such that they contain FPGAs in an FPGA build environment. We're located in Australia, but we have global offices. So we have an office here in London and in New York, and also in Tokyo. So what are we trying to do? We're basically building at the essence of it, we're building a platform on which you can implement FPGA-based applications. And FPGA-based applications have a few implications about what you can and can't do and the sort of capabilities that those sorts of applications give you in the devices. I call them FPGA-based applications, but they're actually usually combinations of software and hardware. You normally have some software component to these systems and some hardware component. So what we do is package up an x86 server, so your standard, a normal, it's our own design, but it's an x86. We package that up with an FPGA in the same box and a layer 1 switch. And I've got a diagram in a second, but a layer 1 switch effectively gives you the ability to implement an electronic patch panel. So you can feed streams of bits through your device with an extremely low latency. So in our case, it takes about 5 nanoseconds to get from one front panel port to another front panel port. We can replicate data. We can use it for as a replacement for passive optical tapping. We can use it as a way of replicating out data very quickly to large numbers of servers or trading systems. It's also very deterministic. So if you're implementing an exchange, for example, it's a very good way of distributing things like market data very evenly and very fairly across the network. So the basis of our platform is partly hardware, which is an x86 server plus a layer 1 switch plus an FPGA. We have a network operating system which we've developed, which integrates very well with the hardware. So this is a suite of tools, an operating system, things like SNMP and authentication and management and APIs and databases and monitoring and all these other bits and pieces that come together to form something that's a high-quality device that can be deployed in any enterprise network. It looks and feels and tastes a little bit like a network switch, which makes it the sort of thing that can be deployed reasonably easily. So we've thought a lot about how to get lots of these devices out into the field to make them manageable and deployable and sort of industrial and enterprise grade. Another component to our platform is IP cores. So we develop applications, and we, as parts of those applications, are libraries which are integrated into our applications. So things like our 10 gigabit Ethernet interface, our 10 gigabit Ethernet module, where we talk to the 10 gig lines and we encode it and we decode it, and we do that very, very quickly. So we've got very low latency IP cores. We do that opportunistically. We applications that we're developing, we wrap that IP up, and we're really developing these things in order to make it easier to develop applications. And then the last thing is containers. So providing a software environment for applications which might be legacy applications, might be things which are a little bit more difficult to deploy, or you want to deploy on a generic operating system. This is the sort of thing that we can support. So I've just got the one slide on what we do, but we actually have a couple of applications ourselves. So we use this platform that we've developed. We use that platform ourselves. We use the development tools which we're providing to others in order to develop our own applications, and we have a couple of applications. One is MetaWatch, which provides timestamping and packet capture services, and then we have MetaMux, which is a very, very low latency aggregation solution. So if you're entering orders into an exchange or a prop firm or an exchange is looking to implement order aggregation, this is a very deterministic, very fast way of doing that. I'll just have one slide on MetaWatch, given where we're at and given where this conference has a little bit of a testing bent. Usually you require, we're talking about capture and replay in the last, for networks in the last presentation. MetaWatch implements very accurate, very reliable timestamping and packet capture. So it can be used as a front end to something like a Corval or Velocimetrics or Capture Solar System or one of these other solutions, which generally don't scale very well, but we've managed to implement it on the device. And again, it's an application which is implemented on our platform. So we have it provides sort of cost-effective network monitoring because it integrates taps with the FPGA capture application. It's got 1 nanosecond precision timestamping and a robust deep buffering solution. So it's quite useful for MiFID II compliance. So back to the platform. A layer 1 switch, a couple of basics. A layer 1 switch is effectively like a patch panel. So if you imagine that all of the inputs are on the left and all the outputs are on the bottom, you can map any input, any outputs back to any input. So you can replicate multiple times. You can, for example, you can see these outputs, these 3 outputs here are replicating this 1 input. So if you imagine you can put a dot in any, as many dots as you like in any row, but you can only have 1 dot per column. You can only select 1 input per output. It's the basics of a layer 1 switch, and it's the basis for all of our platforms or all of our devices. So a software trading system often looks a little bit like this. You have things like logging, you have parameter updates, and you have modeling, and you have all these sorts of processes that go on in the background. But really, when it comes down to it, the bit that people really want to optimize for performance is what I'll call a response engine. And whether this is implementing a matching engine, whether it's implementing a proprietary trading firm's algorithms, whether it's implementing pre-trade risk checking, whether it's implementing back office systems even, what you tend to have is performance critical and non-performance critical parts, and those tend to communicate with each other. So I'll call it a response engine. And effectively what you do when you're implementing an FPGA-based application is something like this. It's exactly the same. You have a response engine which is serviced by a number of software applications. It's just that in this case, the response engine ends up being implemented in a piece of hardware which is configurable. So an FPGA is a configurable chip which allows you to implement effectively any logic you'd like. If you imagine a very large collection of AND gates, NOR gates, NOT gates, it's kind of what it's doing under the hood. But all of that is really abstracted away. What people do is write software that runs on these particular types of chips. And it's slightly different software, but it's software nonetheless. You load a big configuration into these chips, and then they do something, which is almost exactly what you do with a CPU. So it's not the model of operation isn't actually that different to what you would have in a software system. In a software system, you have some performance critical parts of the system. In this case, I call it a response engine. And then you have other things which are probably not quite so performance critical, things like logging, parameter updates, offline modeling, things like machine learning, model updates, all this sort of stuff. So it's not too different. So the advantages of an FPGA-based system, and again, we're talking about what some people call hardware. I would call it software, but it's we'll debate that. The advantages are if it's implemented right, it's got a very, very low latency, and it's a very predictable latency. So what that means is that for sure exactly what the parameters of the behavior of your system are going to be, and that's not true of software. Software systems and modern CPUs are sufficiently complicated that it's very difficult to build a truly real-time system on a modern CPU. They're not really designed for the job. What they're designed for is getting through as much stuff as possible in a short amount of time. They're designed for bandwidth. What FPGAs can be designed for, and it's one of the advantages of the system, is that you can predict exactly what the latency for everything that it does is going to be. It's also possible to make it extremely performant. So in addition to being low latency, it can also get through a huge amount of stuff, and so it can have a large bandwidth. Again, going back to a couple of things that we implement these switches. They have lots of front panel ports. They have lots, they have FPGAs inside of them. They have layer 1 switches inside of them. We split them into different series, so we have different types of FPGAs, Vertex 7 and an ARIA 10, and it basically giving different options for different peripherals inside. And we have developer kits which allow you to program all of those systems. So what I'd talk about a little bit is our E-Series product, and the reason I want to talk about that is because it changes how FPGA systems are built from the point of view of people who are implementing these things in switches. It has the latest FPGAs, UltraScale and UltraScale Plus. They all include the MetaConnect product, as I was saying. And effectively, this is what it looks like inside the box. You've got a MetaConnect fabric, which is basically a big patch panel. So you can take any front panel port and connect it to any other front panel port. But you can also take a front panel port and connect it through to the FPGA. And you could connect it through to multiple FPGA ports. Or you could take taps off those and take them back out to front. But there's a lot of flexibility built into the MetaConnect fabric. So we've connected up, in this particular device, for example, 56 transceivers through to the MetaConnect fabric. We can have up to 56 communication channels between the FPGA and this very flexible patch panel. But what is more important is that we've actually put 2 more FPGAs. So we actually got 3 massive FPGAs all inside the one box. And they can all talk to each other via these transceivers. You could treat them as if they were different nodes. You could have, we were talking about response engines before, you could have different response engines which might be implementing different algorithms. You can communicate with them all independently. They can implement different applications. So we have this idea of a central FPGA which has a lot of transceivers, a lot of connectivity to the network, and then leaf FPGAs which have a smaller number. And we can imagine that a central FPGA might do things like implement pre-trade risk checking, or it might implement multiplexing where you aggregate packets in together. But it also might implement your trading algorithm directly. What we then, but equally we can imagine that on the leaf FPGAs you might update, if you're actually implementing a trading algorithm, you might update those leaf FPGAs more aggressively than you upgrade a central FPGA. Or if you're implementing matching engines, you might implement a matching engine in all 3. Each of them might trade different symbols or might execute different symbols. So you can imagine that you can get a lot of fabric, a lot of FPGA fabric in a one-rack unit device, as close to various other things as possible. And one of the really important things about all of this is that it's physically close together. So one of the limitations to how fast you can make trading systems, not how deterministic, but how fast you can make them, are cable lengths. So you end up, if you've got a 1 meter fiber, you have a 10 nanosecond round trip latency through your 1 meter fiber, you end up with some significant latency. And that 10 nanoseconds is the sort of latency in the modern markets that is winning and losing trades at the upper echelons. For some trades, and for more intelligent algorithms, it probably doesn't make quite as much difference, but for performance, latency critical algorithms, that's the sort of number that's starting to make a difference. You're starting to get certainly sub 200 nanosecond response times in FPGAs. The big game changer in this device, and again, one of the reasons I think it's critical that this FPGA tech ends up being consolidated into the network layer, is that because we can get it all physically close together, we can put very fast, very wide, very low latency communications between the devices themselves. And so we have this central FPGA, which is connected to 2 leaf FPGAs, in this case by 130 I/O pins each. What that means is that you can get up to 4 10 gig streams across in a single cycle. So instead of having a large, I've got a slide on this in a little while, but instead of having a large latency to communicate between the FPGAs, you end up with something really, really small. Again, we're just trying to expand out the amount of fabric you can get very physically close to the patch panel provided by the exchange, or conversely, if you're implementing an exchange or a broker, very close to the communications to the clients. Right, so I thought I'd go on to this is describing what, how we reduce the latency by integrating everything in together. So if you were to have a single FPGA solution today, you'd probably have a layer 1 switch in order to replicate out to a large number of FPGAs. And you'd then receive it in your 10 gigabit Ethernet module, which I call an RX MAC here, receive MAC. That takes a little while. That probably takes 30, 40 nanoseconds to receive it, and then goes through some logic internally in the FPGA, and then it gets retransmitted out another 10 gigabit Ethernet module, gets re-encoded onto a serial line. And again, that takes 20, 30, 40 nanoseconds. So really, if you're looking at one of these systems, you're looking at an absolute minimum of something like 60 nanoseconds just to get from the pins on the FPGA through the logic and then back out to the other side. And that works fine as long as you only want to be on one FPGA. If you're a prop trading firm or something like that and you're receiving market data from an exchange and you're responding to that market data and sending orders back out, you might receive some market data via your RxMac, go through some logic and generate some orders, and that takes minimum 60 nanoseconds. But if you want more FPGA fabric, if you want to separate it out into multiple functions, for example, pre-trade risk checking or something similar, then you generally have to daisy chain them together via the network. So you generally go via your layer 1 switch, you go in through your Mac, your logic, your Mac again, you go through a cable, which takes some time. You go through another Mac, some logic, and another Mac. Basically, you're multiplying up the latency. And that's all well and good, and it gets you more fabric, but it also costs you a lot. So your response time for 2 FPGAs is more like 130 nanoseconds minimum versus 60 nanoseconds minimum for a single FPGA. It means that if you really want to win the latency race, if you're a prop trading firm, or if you want to make your exchange or pre-trade risk checking solution really low latency, you really have to pack the whole thing into a single FPGA. Your latency critical stuff has to sit on a single chip, and that's not great if you want to expand out. It doesn't really scale. If you want to implement, a very large stock exchange, for example, on a single FPGA without having to go through an aggregation layer afterwards, you can't really do that for all the symbols that you'd want to be able to do it. So what we did with E-Series is actually these 130-bit buses allow us to skip the TX-Mac, the cable, and the RxMac. So what we're able to do there is get down to something that approximates the same latency as having a single FPGA, but we're actually communicating between multiple FPGAs. And that's a very powerful concept. It means that we can now expand out things like the number of symbols, the amount of on-chip RAM, the amount of logic that is available to make decisions, the number of transceivers, all these sorts of things, the number of network connections. It's one of the fundamental differences, and I think these sorts of platforms will start to become more and more prevalent over the next 2 years, I would say. Basically what it means is that going via the green line is almost the same latency as going via the blue line. And we go to a leaf to a central and back to the MetaConnect, versus going to the central and back to the MetaConnect is within 10 nanoseconds of each other. Just giving you a concept of how these FPGA platforms have been progressing over the last few years. These are our 3 platforms. K-Series is a Vertex 7 based, so it's an older FPGA. C-Series is an ARIA 10, which is an Intel FPGA. It's a reasonably recent Intel FPGA. And then the E-Series is the ultra-scale based FPGAs, and in this case we're using 3 VU9Ps. And you can see the difference in, particularly in the amount of on-chip RAM. And this is particularly important if you're trying to trade a large number of symbols, or if you're a stock exchange implementing a matching engine where you're trading a large number of symbols, or you have a large book, or whatever it happens to be. All of these things are critical for, these numbers are critical for implementing larger and larger systems. And what this increasing amount of fabric is going to allow is for more and more complicated applications and more capabilities implemented within the switch. So I've only got 2 minutes left, so I'm going to rush through just for. We had this architecture up before, where we have non-latency critical stuff talking to a response engine, which is then talking to the network doing something, and we maintain that architecture. And really what we're talking about here is that we have our non-latency critical stuff sitting on x86 servers, which are off the switch, and they can communicate with a switch which is actually actively participating in the trade. And again, it's really important that this is close to the network fabric. There's a couple of quick thoughts I had. One is PCI Express. I've got this personal vendetta against PCI Express. It's a horrible thing, but it's the traditional way that you implement FPGA-based applications. A more modern way of doing it is to talk to an FPGA via the network, much simpler, easy to deploy. And really what we're talking about is having lots and lots of x86 boxes communicating via the network with a network switch, which is then actively participating as part of the trading solution, which looks a lot like this. So again, we just have a whole pile of x86 boxes talking to a network switch, which talks to an exchange. Nothing particularly different when it, from the physical side of things, but when it comes to the actual architecture of the underlying trading solution, we're getting the switch to actively participate, and the switch is actually the response engine. And we're moving that response engine now extremely close to the network fabric, literally extremely close to the patch panel in the rack that serves it. So that's all I've few things that I've had to talk about, but if there's any questions or anything else, then, or if you think I'm completely wrong, I'd love to know about it.
Thanks, David. Let's do the questions.
Hi, thank you. I have a question. What type of languages are supported when you program on FPGA?
So FPGA, I mean, this is not a problem we're trying to solve, but we have an interest in it because we want to make it as easy as possible for FPGA, for applications to be written for our FPGA. So the traditional hardware development languages would be things like VHDL and Verilog. They're effectively describing logical processes. So they're the same language that would be used to design ASICs or CPUs or something like this. What has been happening recently is a whole lot of work in high-level synthesis, where we're looking at there's people who are trying to translate C and C++ and OpenCL through to these underlying languages. The reality is that if you want to implement a really optimal system, you're going to be best off going down to the lowest layer, much as you're best off going down to assembly, or probably not assembly, probably C these days, but C as a proxy for assembly, whereas you wouldn't write a high-performance system necessarily in Python. You'd write certain sections of it, or actually, much as you have in Python, you'd write certain sections of the code in Python. The thing that controls everything will be written in Python, but then you'll have C or C++ modules which are compiled and interface with that stuff. It's exactly the same sort of situation here, where you implement the performance critical bits in the lowest level language, where you have the most control over the hardware, and you can really specify out exactly how the hardware is going to behave. And then you'll write the non-latency critical bits, but possibly the logical bits or the more productive bits, they'll be written in software probably, or whatever you're most productive in. So going back to what languages, there's also a number of other tools, things like P4 and other sort of, and there's also actually Python, which compiles down to HDL. There's a lot of work going in at the moment, and particularly with Intel's acquisition of Altera, we expect there to be a significant increase in the number of tools available to end users to basically ease the effort of developing these applications. And then, of course, lastly, then there's specialists in this area who can develop applications which will run on the FPGA itself and implement the core of what's required on the FPGA, and then you can use that as a building block on which you can coordinate. Much as nobody goes away and re-implements NumPy every time they want to run a simulation in Python or implement big data in Python. They use a coordinating layer on top. Much is the same in an FPGA, where you have an FPGA application which is implemented and then coordinated by externally written software, and the value is really added by that externally written software.
Along that lines, is any of this stuff open source?
There are open source FPGA applications. There's, for example, the NetFPGA project, which comes out of Stanford and Cambridge, and there's a number of academic institutions which surround that. There are a number of sort of FPGA applications which are open source. There's the OpenCores website, which has hundreds and hundreds and hundreds of open source projects written in VHDL and Verilog. I think for trading, you're really talking about people that have written it in-house because they've put a heck of a lot of work into that IP and they're not keen to give all that IP away. But there's certainly examples of how to write FPGA-based applications, and one of the things we do, of course, is put together a few example designs which allow you to see how things might look. Our example designs don't add a whole lot of value. We're really providing just the platform, and our applications are not open source. We value our IP as much as the next person. But there is a lot of code out there.
Thank you. I think there's another question over there.
Sure. Is it? So when you program on the x86 side of things, right? I mean, say you use C++ or C, I mean, how do you reason about the latency of the resulting algorithm, right? So you have extremely low latency hardware underneath, right? But ultimately, the complexity of the algorithm is such that it can obviously add quite a lot in the worst case. I mean, is there a strategy in terms of, basically what you care about is end-to-end latencies, right? And it's easy to screw things up in a hurry, right? So what strategies do people use when reasoning about their end-to-end latencies in the face of these potentially complex algorithms?
Right. So I guess it's a little bit like what if you imagine that you're writing a program that runs on an x86 and you do a memory read. And under the hood, the memory read is going through to first the registers, and you're checking whether they're in registers, and then it's going down to a layer one
it goes
cache.
through 2 levels of caches, remember? Right?
Probably 3 layer caches, so it goes down to level 1, and that takes you a single cycle, and then it goes down to layer 2, and it takes you like 10 cycles.
So you have expected completion times, and you get a reason about those, which becomes pretty difficult very fast.
Yeah, and it certainly does. So what your goal therefore is to pack everything into layer 1 cache. And if you can assume that your application, you know whether your application fits into layer 1 cache or whether your data fits into layer 1 cache. And even at a finer grain, you're looking at cache lines. So if you can get all of your data in a single cache line, you know that you've got a deterministic latency as to how long that'll take to load in. A similar thing is true of FPGA-based applications, or even your software applications, where you architect where you have this very fast response time engine, and then you have slower things that do things like logging. You don't put logging in your fast path, but it has to happen off because you want to be able to see what happened in your devices. So I guess that's one thing. You know what the behavior of the system is going to be. It's not just the same way as you know what the behavior of your layer 1, 2, and 3 cache is in an x86 in a given particular processor. So that's one thing. Another thing is that it's measurable. So if you want to see what the response time is, you can take taps off these observable network links. So if you're, for example, talking to your FPGA via 10 gigabit Ethernet, you can tap that 10 gigabit Ethernet line using standard network monitoring tools. You can reason about how long the FPGA took to respond by looking at what went into the FPGA and what came out of the FPGA, whether that's coming in from the software layer or whether it's coming in from external network links.
I mean, assuming you have a representative distribution of inputs available to you, which is always a question, right?
Well, yeah. So if you have, we have 90 up to 96 ports on our device. You can have a whole pile of exchange links coming in here into that device. You can read them in on FPGA, even in the core FPGA and the central FPGA. We've got 56 transceivers, so there's a lot of bandwidth and a lot of connectivity, a lot of different network links which can be used. But equally, those network links might talk to x86 servers, and those x86 servers, packets and messages from those x86 servers themselves might generate trades. If you were to put a manual order in, for example, the FPGA might still be the thing doing the manual order. If you wanted to do an iceberg order or something like that, you could, if you're looking to do execution using an FPGA, then it may well be triggered by packets from the other end. They're not particularly latency sensitive packets, but the bit that's latency sensitive is usually the response to what's going on in the market. But those orders might be triggered by external events which are provided from the non-latency sensitive side of things.
So the answer is extensive testing, essentially. That's what you're saying.
I think it comes down to, if you want to know about the latency of your actual FPGA application, and you can define what the behavior of your FPGA application is, the way you build an FPGA application, it has an inbuilt concept of timing. You know that a response will take exactly 30 cycles, and 30 cycles is probably, usually you're running a clock at, 156 meg or something, and maybe 30 cycles is 6 nanoseconds per cycle, and you work out that that's 360 nanoseconds. So that's your response time, plus the 10 gigabit Ethernet MAC at either end. So there's a little bit of, you can model the whole thing out. It's much easier to model than a software system because it's very, very well defined exactly what happens right the way through, compared with these very complicated cache architectures, things like TLB misses, things like, pipeline misses and reorder buffers. And, there's so much complexity in a modern CPU that it's just impossible to actually understand what the performance is going to look like. Whereas in FPGA-based systems, it's kind of fundamental to how you build them that they have to take the amount of time. I mean, assuming you build them with this in mind, you could, for example, implement a CPU inside an FPGA and then run software on that CPU, and that would give you all the same problems. But assuming you have a bit of a think about how these things are going to be implemented, you can understand very, very well what the latency is and what the bounds on that latency is and what the distribution is. And then usually what we do for our applications, for example, our MetaMux application, we'll model it out, we'll check what we think the latency is going to be, and then we'll measure it in real life and check that they match. And if they don't match, we usually assume there's a bug somewhere, because it really should. We can look at it using MetaWatch on the line, we can measure the latency through it, we can stimulate it using replay in order to work out, it should behave exactly the same way either way. It's not like a CPU where you have millisecond outliers because an operating system timer tick went off halfway through your trading algorithm. You don't get those outliers. Our MetaMux application is plus minus, I think it's 3 or 4 nanoseconds, plus minus a cycle. You would never get those sorts of, that kind of determinism out of a software system.
Thanks a lot. Any further?
I like the fact that you're trying to put everything close together, because it is possible today and it can bring some benefits. You also mentioned Altair acquisition by Intel, and then you dislike PCI Express. Do you think the acquisition, and I heard rumors about having FPGA and x86 processor on one chip, do you think that's going to change anything, like for you or for the industry in general?
Yeah, I think it's going to change a lot. I think that's going to be huge. I think that you're basically talking via a cache coherent protocol between an FPGA and the CPU, so it's going to be much tighter integration. You're not going to have things like having to re-enumerate the PCI Express bus when you reprogram the FPGA, so you can get a lot more dynamic with how you treat. You can treat the FPGA much more like a software resource, the same way we treat them in our devices, compared with how you traditionally treat a FPGA-based application, where it's a lot more like a poor man's ASIC, where you're trying to simulate a piece of silicon which was actually built as a piece of silicon. I see FPGAs as a lot more exciting than that, because they can be treated as software resource, because you can reprogram them and change how the hardware is configured, and you can do that on the fly. Using PCI Express means that it's a lot more difficult to do that. So I expect Intel to put a huge amount of work into turning the software environment which surrounds their FPGA implementations in their combined systems. So I think it's going to be phenomenally exciting to see, especially as these FPGA-based applications are then deployed throughout the data center. So they become a lot more ubiquitous. You'll get a lot more people with a lot more talent for building FPGA-based applications. There'll be a real market for IP cores and different applications which can then be used as these building blocks to be directed by software systems.
But you still see an opportunity for your devices in cooperation, in synergy with the integrated CPU and FPGA?
Yeah, absolutely. So I guess we see ourselves as being the FPGA vendor of choice in the network fabric.
Thank you.
Yeah, perhaps a silly question, but I'm not that at home in hardware. But
Hardware, gateware.
Yeah.
Hardware is resistors and inductors and
Sorry, man.
steel
This
and
just
heat
proves the point.
sinks
I'm
and
not
things.
at home. But what I do see is that people also invest in using graphical chips to speed
Right.
up stuff, right? So from your point of view, is a graphical chip, is that more on the CPU, so undeterministic, or is that also more in line with the FPGA thought?
It's a more specialized chip, but it effectively, what a graphics coprocessor comes down to is being a very, very large number of programmable, but serially programmable entries. So almost a very, very large number of very specialized CPUs. So it's less flexible, and you're built into a certain programming model. There's also problems with getting information into and out. So you've got non-determinism getting into and out of a GPU. So it really comes down to horses for courses and the right tool for the job. And FPGA is very, very good at being very close to the wire. So you can have bits come off a wire, go through a transceiver, and then be ready to go in an FPGA right there in the fabric. And you're talking 20 nanoseconds from the wire to being ready to go in the fabric. And for that to be a very deterministic amount of time. With a GPU, you'd probably have to go via a network card through a CPU, export the data to the GPU, back to the CPU, back out of the wire. So you've still got this general purpose CPU, which is shuffling data around. I mean, that might change. Someone could build a trading optimized CPU, which might look a little bit like a GPU, but the reality is that you could do that on FPGA, and you could tweak that programming model with, even if you were to implement a trading specific CPU, and you had an instruction which was like send fix order or something. You could still do that. You could do that in an FPGA, but you could still optimize it a little bit better and make it more efficient if you actually change the hardware itself on the fly. So you can still get things better if you work at a lower level, and probably more importantly, you can get them more deterministically. So you can make it more consistent, more understandable, more modelable. So yeah, GPUs definitely have a place in the world because they've got this bandwidth capability. They can get through a lot of calculations very quickly. FPGAs are a lot more controllable, a lot more precise. Where a GPU is a little bit like a Mensa, a FPGA is a little bit more like a razor.
Thank you very much. David Snowden,